Hey there, everyone. How's it going? Gonna run you through this lecture that covers angular kinetics, in particular, this idea of equilibrium. And most importantly, we'll get into torques and similar ideas such as conservation of angular momentum. If you're wondering what's going on here, this is a future semester, something like that. Actually, broke my collarbone, as you can see here. So I just have my sling on to kind of protect my arm and collarbone that way. Anyways, thanks for bearing with me. I'll only have one arm to kind of use and mouse and stuff like that, so I won't be able to work through any of the equations on the whiteboard feature. That being said, afterwards, there's one equation in particular that I'll post like a little supplementary PDF that kind of solves things step by step, and I'll get that up to you all as soon as possible. Okay, cool. So let's kind of dive into this. As always, have some review questions. That being said, this semester we did not particularly cover work and energy, which is okay. If this was the semester that you did, you can start working through these questions now. Give you a little moment to pause, and then I'll go through these. So the first question, the greater the height in objects, the less potential energy it has. Is that true or false? Well, an energy or the potential energy of any object, of course, if we look at our potential energy equation, is definitely dependent on height or how far above our zero level uh, the object is. So um, it will have more potential energy the higher it is. So that would be false. And then if we look at our next question here, it's asking about kinetic energy. So we can go over to our kinetic energy equation, and we say that half of the mass equals velocity squared. So if we're tripling our velocity, we are going to essentially square that rather than just multiplying it. So it's not directly proportionate, right? We're going to set that by a squared factor. So if we triple our velocity, that's going to have a greatest factor. We'll increase our kinetic energy by 9 times. So we have our 9 times velocity there as the best way to increase an object's kinetic energy. Okay. Next question, 3. Again, give you a couple moments to pause and work through this. A couple of different ways that you could work through this question. Uh, more or less for the first one, we get to plug and play for how much work was done. If you note here, because the bobsled is working horizontally or on a horizontal plane, we get all of the force produced happening horizontally. We don't need to worry about what theta is for that particular scenario. So we can just take our force, which is 800 newtons, and multiply that by our distance, being 50 meters, and we'll get our work there. Once we get that, that's how many kcals that is. So we use our conversion unit here, and we essentially multiply whatever our work was in joules, or sorry, divide that by 4,184, and we'll get how many kcals that is. Yeah, and then once we're here, we can kind of pick or choose because we'll have our work in joules and kcals, and whichever one we want to use, that's fine. I don't know which one you picked. Both are optional options as long as you stick with the same units. We can put it into our efficiency equation here. So the amount of work that we get out, so that's mechanical work, so the work from the sled actually getting moved relative to the work going in. Um, yeah, we can calculate that. And I believe we end up getting something around 30%. So, okay. Yeah, obviously feel free to email me if you have any questions about those. Okay, so getting into this idea of equilibriums and torques. They're somewhat related, and we use actually equilibrium to help calculate torques. So it also goes into building and bridge design when we're talking about equilibriums. They're kind of stable, and so we see, or we'll come to see that all these buildings and structures stay in a stable equilibrium. And in regards to torques, we're really talking about any angular motion with force, right? So all our joints in our bodies have a pivot point. Typically, we don't really have any translational joints, and therefore, anytime we're moving our limbs or moving our body, it's all torques that we're talking about, and we'll dive into that. Okay, so here's kind of the outline for today. I'm going to go relatively quick through equilibrium and balance and stability, kind of related ideas. We're going to spend a bit more of the time on torque, moment of inertia, and conservation of angular momentum. And again, as always, feel free to shoot me an email, set up some office hours to chat about these if you need a bit more coverage of them. Okay, so equilibrium, what is it? Well, we have two different types. We have static equilibrium and dynamic equilibrium. If we look at the static equilibrium examples, we more or less see that our net external forces on all our axes, so our x and y, even z axis here, they all equal zero. So kind of like in our one example of our person standing here, we have their weight and normal forces equaling for equal a net zero. So that's fine. We wouldn't expect too much movement. They're just staying stationary. If we look at the hockey stick, and again, you can imagine from directly, equally on both sides of that stick, we have equal but opposite forces, opposite direction forces. Uh, again, we have a net zero. We wouldn't expect anything to happen. There's no movement. The stick just stays where it is. Slightly different would be our dynamic equilibrium. We have something in motion, but all of our forces on our x and y axes, again, if you add up all the entire normal forces there, would equal zero. And therefore, even though the vehicle's in motion, we wouldn't see any changes in its motion. Remember, if we think back to Newton's laws, things in motion will stay in motion unless acted upon by an external force. In this particular case, yeah, we have a bunch of forces going on, but they all equal zero. And so we wouldn't expect a change in the vehicle's velocity unless, for example, we started braking, the drag force increased, the some other net external force started changing the vehicle, maybe accelerating more, therefore increasing forward direction force. So again, all kind of equals zero. The one thing we haven't been considering so far with these is rotational force or a rotation force. And what that includes is torque. And so without giving a full definition quite yet, or just keeping that in mind, you can kind of envision the scenario with a hockey stick. So for example, if we change where the forces are applied, so instead of directly across from each other like it was on the last slide, we kind of move them apart. If the stick's lying flat on the ice, you can kind of picture like if I'm poking that way from above, this way from below, we'll see the stick turn, right? And so that rotational force is torque occurring, right? So we can't just say our x and y forces equal zero, and therefore we will have this stable, non-changing slash object not moving kind of scenario, because that's not true anymore, right? So yes, we need our net forces to equal zero on our x and y axes, but we also have to say our net torques must also equal zero. So if we look at an example here, we have someone doing an iron cross. We're going to see a video of someone doing this for the world record, or what was once the world record. Uh, they're not moving. They're static. They're staying in the same position. They're holding this position. So again, the kind of like rotational forces or torque that's occurring at their limbs. For example, the pivot point is their shoulders. You kind of have these forces occurring away from that pivot point. So that's creating a torque. Yeah, all of that is going to be also equaling a net zero, as well as the up and down forces on the, let's say, x-axis, and any lateral along the y forces are also going to be zero. So we can say that is a true equilibrium. Yeah. Now, the one thing with equilibrium that will help later when we're talking about torques and calculate things with torque is exactly the point where we can make one side of kind of an equation or this like approach to figuring out net torques equal the other side, and we can solve if we know the scenario is in a stable or in a net zero equilibrium. We'll get to that though a bit later. Yeah. Okay, so balance. We all have a pretty good idea what that is. Uh, we use the term fairly regularly when we're describing movement and motion, but let's look at it specifically. What is it by definition? Well, it's the maintenance of equilibrium and of an object or a body, but we essentially have the center of gravity. For most, we can also kind of interchange that with center of mass. And we can say that has to stay somewhere over top of the base of support of the object or body that we're speaking of. Now, if we kind of look at the scenario, this kind of makes sense. You know, center mass is somewhere in the hips. It's a little lower for women, a little higher for men, on average, typically for most across populations. Um, and yeah, whether we're in a stable equilibrium or a dynamic equilibrium where there's motion, we always tend to have the center of gravity over top of the base of the support. And in this scenario, you know, it kind of changes. We do see the center of gravity outside of the base support for this particular individual with a walker. But what we will do here is we actually take the base of support and extend it to be under the walker as well. Okay. So even though this illustration shows, oh, it's outside of the base of support, it actually is extended to the walker. And, you know, we can kind of imagine taking the walker away. And if our center of gravity is out front, we have our poor individual here likely to kind of topple forward or have to correct for that loss of an extended base of support by standing upright again, right, to prevent falling. Right. A few other ways this will creep up or prop up that you might see uh, out in the world as you analyze human movement and look at people moving or standing. You know, if we have our nice posture here, someone standing with a good neutral spine, they don't have any postural deviations, you know, we'll very predictably have the center of gravity right over top the middle of the base of support. But a lot of folks have slightly different postures or even body compositions, and so that'll change their postural stance and therefore change where that base of support is more commonly found. So for this individual, we see that it's moved posteriorly a little bit more. Yeah, and it's not too uncommon. And we see even farther back, right? So this would be someone like leaning back quite significantly. And we see this in different postural stances that come up. You know, if someone has a very kyphotic or like curved spine. Sometimes, often that's found with a lordotic. So we kind of have this big S curve that we'll see laterally in someone's posture. And more or less the two curvatures are trying to cancel each other out. And so you could still have a relatively midfoot center of gravity or over top of that base of support. But yeah, we can see deviations there. Sometimes we'll use 4-point, so feet or knees and hands in like a clinic or gym setting when we get people exercising. And what that does is help stabilize people and have a greater base of support, therefore able to achieve some more things depending on what we're trying to do for them. A stable position is one that's a little bit more easier to move in for individuals that might have poor balance. And if you remember back to the start of the semester when we did a Trendelenburg, so a single leg stand test, people that are able to have their center of gravity just to the edge of their base of support, so their foot, can usually keep their hip tucked underneath them, right? We kind of spoke about the hip going out. Another compensation that you'll see that would be a positive test for the Trendelenburg is people having to actually shift their whole torso over so that their center of gravity is more over top of their base of support here, right? So again, rather than kind of being at the edge of the foot, we get it more midfoot, and that's easier for them to stand. Uh, Again, a few things going on there potentially. So yeah. And the last place we kind of see this idea of center of gravity come up that we'll use as an example for you um, is actually with high jump. Uh, yeah, this illustration is pretty good, but essentially over the years in high jump, we've seen an evolution of technique. And really what this increase or change of technique has done is added to the capacity for um, high jumpers to be able to change where the center of mass goes or travels either at or under the bar that they're trying to jump over. So here's kind of how it happens. So we have our first three most common, or let's even look at the first two, the scissor and the Western roll. So there's blue and red. Typically, when athletes are jumping over the high jump bar like this, their center of gravity or mass typically remains at or above the bar. So you can see all this person's body, a lot of it is above the bar, right? So their center of mass debatably kind of resides somewhere there when they're doing these jumps. And sure enough, we see that these are relatively lower jumps in height relative to these other two methods, right? Then we get into the straddle. So the person kind of like rolls over the bar. This is them clearing the bar, or I guess maybe coming over this way. But for part of this roll, they're as they're trying to get most of their mass over the bar, because their arms and legs are kind of on this side underneath the bar relative to over, we can actually keep the center of mass roughly at bar height as the body passes over it. Okay, so here we kind of saw an increase in capacity to jump higher because of that. And then last but not least, we have Mr. Fosbury that came up with the Fosbury flop, where people go backwards over the bar. And at first, this was like people were freaking out about this. They're really concerned about athlete safety. Like, oh, what if people land on their heads and necks, and we see all these injuries occurring? But sure enough, it just kind of became common practice as people, well, I wouldn't say perfected the technique, but became more proficient at it. We saw greater and greater heights being able to be achieved. The reason for that is athletes were able to keep more of their mass below the bar, even as they're passing over it, right? So again, if we kind of think people lay their head back and over the bar, that's why I don't think this illustration is great. This person's head should probably be a bit more down here. So we have way more mass traveling below the bar, essentially the entire jump. And so we see their center of gravity kind of there, roughly. And because of that, you can technically jump with the bar being set higher, right? So again, this technique change just kind of uh, leverage this capacity to move where our center of gravity is outside of uh, where our body actually is traveling, and therefore be able to jump higher, which is pretty cool. Yeah, so some application there for our center of gravity in sports. Um, right, so we've talked about equilibrium, spoken about balance, and now we'll speak in brief about stability, which is a little bit different. Stability is the capacity to resist change. So again, balance is maintaining equilibrium. Stability is resisting change, right? Different than inertia because it's based off the position and center of gravity. Okay. In particular, where is our center of gravity relative to the normal force? And as a callback, the normal force is anywhere where there's contact between two objects, right? So, um, yeah, we'll start in our stable equilibrium. So our stable equilibrium, what we see is it's called a restoring force. So we have our center of gravity here and our normal force because there's in contact with the pencil there. So what we'll see is a restoring force back to the flat side of the pencil. So the pencil will upright again. Presumably if it's not moving too fast, it'll just stay upright. And that's great, right? We kind of have that pivot point. Hopefully you can kind of vision that. So we have the restoring force. Here we see that our center of gravity is outside of our restoring force. So for example, it wouldn't pull the pencil back to this flat part to stand on that end of the pencil. It's essentially going to pull it right over and fall onto the side. So, if we started with the pencil lying flat down on this side, that would be a restoring force, but in the scenario, we're kind of picturing the restoring force going back to here. So it essentially caused the pencil to displace and topple over. Okay. Again, it's relative to where the normal force is. In our last scenario, we have something called a neutral equilibrium. So with the pencil lying on its side, we can see the pivot point or the axis point actually running the length of the pencil through the middle. So that's where its point of rotation is, right? If we were to add some force, the pencil would roll. But we'll see the weight force or the weight of the pencil pushing down is met equally along essentially the entire side of the pencil that's in contact with the table with the normal force. And so because of that, we see that these two forces kind of meet this like uh, uh, I don't want to say net zero, but they more or less are in opposition to one another. So we see this system, is what we call that, independent of uh, essentially any uh, restoring forces or anything, right? So it's just kind of constantly in this state that's independent from any displacement that we put on it, whether we kind of push it one way or another, it's going to maintain the same kind of equilibrium. Okay. Okay. Yeah, and I think we can kind of imagine this, in different scenarios with the human body a little bit, in the sense that we can use stability to help resist change by actively changing our position. And so one different ways we can do this is we put our feet wider, so we have a wider base of support, therefore, relative to the normal force, our center of gravity isn't displaced out that, beyond that, causing further displacement. And we can also get our center of gravity lower, which makes it a little functionally harder to get outside of those points of where the normal force is in contact with the ground. So again, another way to say this is we just have more stability. So the last way to touch on is if we have a cane, so we increase the points of contact, we increase where our base of support is, either the size or width. We also therefore increase the difficulty it is to get our center of gravity outside of those normal forces. Therefore, we always kind of have this restoring force to keep us more centered or more stable. Okay. Tried saying that a couple of different ways. Hopefully one sank home for you. Okay. Okay, let's dive into torque. This is, I don't know if I could flash the screen or something like that. This is going to be really, really important here. This is a big topic, definitely important to know torque, how it works, how to solve for force and torque, etc. But we'll kind of get to that. Again, torque is so huge for our body because I'm just going to play this video. Because our joints have pivot points. They all are pivot points. And when we're talking about a torque force, we're really talking about things around a pivot or axis point. Okay, so here's our dynamic or our equilibrium occurring, our static equilibrium. Any torque forces are equaling zero, and any forces linear up or down are all zero, right? This is also so impressive. If you've ever tried this, you know how challenging 1 second is, or a fraction of a second, let alone which is now a world breaking record. Previously, it was like 21, 22 seconds. And looks like this guy goes 33. Yeah, nice, super impressive. But again, the things we're kind of keeping in mind there is, for example, his shoulders are pivot points. So we have rotation that happens around a pivot point, right? We're talking about angular motion rather than something linear. And that happens with our body through most all movements that we produce is all angular, right? So let's take a look at what exactly torque is. And again, if we ignore all this writing for a second and let's just take a look at these equations. Again, torque is a rotational force or um, kind of equivalent um, to force when we're talking about angular or rotational motion. So if we just go through the factors that contribute it, we see that torque is uh, proportionate to the amount of force that is applied to something that can rotate. It depends on how far away from the pivot point or axis point that force is applied and the angle at which that force is applied to that rotating object or the object with a pivot point will tell us how much torque we have. Okay. All right. We kind of give you a couple more pieces of information and then I'm going to show you an example which I feel highlights these points really, really well. Okay. Yeah, so when we have torque, it can either happen in a clockwise or counterclockwise way. And if we really break it down, if we're applying a torque directly 90 degrees to something or perpendicular, we're really just looking at the R value, which is the distance from the pivot point. Again, this is the same kind of R value or radial arm length that we've been dealing with often in rotational motion, and the force applied as it fully is, okay? So what we get for units for torque is Newton meters. If you're familiar with vehicles and stuff like that, you'll also often hear the amount of torque a vehicle has in um, foot-pounds or something like that, but that's not metric or SI. So Newton meters is what we use. Okay. All right. So let's look at this practical aspect of these variables that relate directly to how torque is produced and what torque is. And that should help highlight exactly what this equation is all about. Okay, so we're going to use the door as an example. We'll just kind of go through each of these scenarios, looking at each of the variables. So the first one is and again, the force is the same magnitude in all of these variables unless otherwise stated. So we can kind of see we're applying a force perpendicular, so exactly at 90 degrees to the length of the door. Here's our pivot point, it's the hinges, right? So we have an R value. An R value that is the distance away from that pivot point where the force is applied. Good. And I think intuitively, if you think about where we go to push a door, it's usually farther away from the hinges rather than closer, right? What is the reason? Well, we can cause a rotational torque to occur along the axes of the hinges. A lot easier if we push farther away, so at the outside of the door, rather than closer to the hinges. Okay, so again, that's why we have door handles out at the far side of the door. Okay. All right, and then again, directionally, we see this as a negative force versus a positive force. So to be more clear, typically you would say clockwise or counterclockwise, right? This would be counterclockwise, that's a clockwise force. Okay, you can use positive and negative though, for sure, depending on your uh, system that you've depicted. Okay. Okay, the other thing that we should note still is these forces are happening at 90 degrees. So another way to say that is when we have a sine of 90, we essentially get a value of 1. So whatever we're multiplying our R and F value by would be 1 because sine of 90 is 1. So we can essentially get rid of the sine theta if we know we're applying the force perpendicular to whatever the object is, okay, or person or body, okay? So we can use this shortened equation. The upside down t just again means sine 90. So okay, you could just write RF though for sure. All right, and again, that's only if it's at 90 degrees. We'll see why in a moment. Okay, so here we have another force. Looks like it's less force applied to the door, but still at the same distance as this scenario. So our expectation of what the torque would be relative between these two examples would be that we'd have less torque, right? So if we look at this F value, or similarly this F value here, if F goes down, torque goes down. It's proportionate, okay? Because we just are multiplying all these factors together. Okay? All right. Hopefully it seems kind of easy peasy straightforward so far. Okay, let's go to an extreme example of angle for a second. Okay, so we're gonna go from B over here to window F. Okay, so if I was to take a force, and you can even try this at home if you want, but you walk up to the door and the first time you can push at it at 90 degrees directly on, see how the door moves. Maybe you can just imagine this. For this scenario in F, put your arm more or less directly along the plane of the door. And then again, at that same amount of force that you applied, just try to push. You don't really make contact with the door, right? Because you're going along the surface of the door, right? So again, look how this force is being applied. It's still the same distance out as this scenario, right? Still the same point, same R value, but it's being completely pushed at kind of 180 degrees or 0 degrees, we could say, right? So what would happen to the door then? Well, we wouldn't see it move. Why? Because none of the force was actually translated into a direction that would cause torque at the hinges. So another way of saying this is if we go sine 0, because our theta is 0 now, because we're going along the plane of the door, we are not putting any force in any kind of direction that would cause rotation at the hinges. So along the axis point, there'd be no rotation. Therefore, if sine 0 is 0, we'd zero our force, we zero the kind of all values over here, our torque would be 0. So we wouldn't see the door rotate at all or pivot around the pivot point. That kind of makes sense, right? All right, let's look at another scenario here. So now let's go somewhere in the middle. So we just kind of glance, we give a glancing blow. Same force as, let's say, scenario 1, same direction from the door, so we're pushing it in a counterclockwise way. Our same R value, so we're the same distance away from the pivot point right here. But now we have some weird fraction, let's just say half, so like 45 degrees. So we're not at 90 degrees, we're not at 0, we're somewhere in the middle. So we kind of give a little bit of a glancing blow. So again, if we're thinking about taking something angular and look at two axes, so splitting it up into like an X and Y axis, we'll see some of the axis of that force will be translated in a direction that will cause rotation or cause torque at the axis point, okay? And again, it's a fraction of what would be if we're at 90 degrees. Okay, so 90 is 1, 0 is 0, 45 is about half. It's somewhere in the middle of those two. So the torque we'd expect in this scenario relative to this one would be about half, and then about, well, I guess can't really say twice as much or whatever, but it would be halfway between these two scenarios where our angle goes 90 to 0. Okay, so it's somewhere in the middle. Okay, hopefully that kind of makes sense to you too, right? If I directly push a door, it's going to rotate or have more torque than if I just give a glancing or a fraction of that force. Okay. All right, last scenario here. I kind of spoke about it when we're looking at our first scenario, but we're going to change our R value. Okay. So again, if I'm looking here, 90 degrees, that means 1. So I can just even use this equation. So my force is the same between A and C, but my R value, let's say, gets cut in half. It looks more like a third shorter, but let's say it's out here. This is about halfway relative to this as far as its R value. So the force is now being applied in the middle of the door rather than at the end. What would I expect would happen to my torque value if F is the same, but R goes down? I'd expect my torque to go down, right? I'd see less rotation because there's less rotational force, aka torque. So if I see less torque there, again, the door is going to move less, and that should make sense. And you can try this too at a door. It feels weird, it feels awkward going up to the door and trying to push it really close to the hinges. Like if you try to, as best you can, approximate the same amount of force kind of being pushed at the end of the door versus say even like extremely close to the hinges, you'll notice like how much of a difference that makes as far as the door actually closing or not, or opening, depending on where your starting position is. Okay. Okay. So that is torque. That is the idea and concept of torque as it's applied to a door, right? And again, we use them every day, so hopefully that feels a little bit more familiar, kind of as an example. All right. But I mentioned before, the human body has torque occurring all the time, all over. So let's take a little look-see here. If we look at a knee, okay, so structure is function, and what we have come to find with our knee joint is a good illustration of how torque can work. So here we are, we have our normal kneecap here. We have force being applied way at the end of our kneecap by our quads. And of course, muscles always contract. And because it's a tensile force, the force occurs in the direction of the rope or the muscle in this case. So we see a force being pulled up towards the hip as the quad contracts or shortens. Again, muscles only shorten. And so we have our R value. So the pivot point of the knee, I might argue that pivot point happens a bit more there, but in this illustration is here. Pivot point happens there. We have distance and R value up to where that force is applied, okay? And again, if we're looking at our torque equation, here's F, here's our R value, and whoa, that's happening at 90 degrees. Great, that is exactly how we want to apply force, idealized to maximize our torque that we get out of that. Perfect. So we can even just use this equation because again, sine is 90. Great. Now, if we happen to have an injury where our kneecap slides over to the side, for some people, they have kind of this like it's called a patellar tendon or patella tracking syndrome, essentially. A lot of runners can get it if they get quad inequality and stuff. But essentially causes the patella to track over to the side a little bit more than not, depending on what you have going on your knee. Sometimes it's lateral, sometimes it's medial. And here in this example, we have something called a subluxation or uh, a luxated patella. So the patella actually slides over around to the side of the knee here. Now, if that was to happen and the quads still apply to force, we make an assumption, the force is still being applied at 90 degrees, but we'll note that the R value is significantly lower. So aside from all the pain and discomfort this person would probably feel, um, we also see that the torque being produced at the knee is significantly less, even for the same amount of force produced, because our R value is short, right? Here's our R value in the green, approximated, here it is here. So again, R value goes down, torque goes down. Okay, so our bodies are kind of cleverly designed that way. We can also see the shortening of R value and changing of angle of how force is applied if we happen to get something like osteoporosis, um, or in this case, someone has had their patella removed, but usually they'll replace it. There's prosthesis or that we can use to do that. But again, we kind of get the shortening, so our angle isn't at 90 degrees anymore in this case. It's kind of more uh, angular depending on the position of the knee, rather than staying at 90 the whole time. And our R value is slightly shortened by about that length. Okay, so again, we get some really, let's say, uh, functionally set up systems in our body that our biology has managed to sort out to maximize our efficiency and torque at our different joints in our bodies. Okay, pretty cool. All right, this is like a pause and think moment. Again, you can pause and think about it here. Give you a couple seconds to do that before I give you the answer. Okay, so if we compare all these doors, they all have different R values, and essentially it's asking which requires the most perpendicular force. So assuming that the torques are all equal between all same to actually get the hinges moving, or the torque that you need to overcome, we're essentially looking for the one with the lowest R value, therefore needing the highest force produced. Okay, we're assuming 90 degrees application of force on all of them. We can use this equation. So again, the lowest R value will have the highest force, assuming all torques need to be equal. And sure enough, here we have our Hobbit door. Door handle's right in the middle, whereas the force from the hinges on all these other scenarios are farther out. Therefore, this door would require the most force. Okay. All right. Yeah, again, for some of these equations, I'll give you a way to solve them on a PDF later. Again, unfortunately, if I try drawing with my non-dominant hand on the whiteboard, I think you'll the scrawling is already bad enough. You don't, I don't think this would be much helpful. So much more helpful. So I'll try to post that worked out for you, kind of line by line, typed out afterwards. But I can walk you through this one at least verbally. Um, there's a couple of different ways you can solve this. You can literally just identify all the clockwise and then the counterclockwise forces or variables involved. You can see that we're assuming here, although it doesn't state it, I usually state it verbally, that all the forces are applied perpendicular to the door. So we see the person going clockwise, we go 3, which is our R value, times our force, which is 200. So that's 600. And then we have our counterclockwise force, which is 1.5 meters times 400, which again, I believe both equal 600 Newton meters. I believe that's how I set this up. And therefore, if we have the same clockwise as the counterclockwise forces, what we end up getting is uh, a net zero scenario. So we have this equilibrium and we don't see the door move. So What a instance here occurring at the door, right? Um, yeah, so that's how we'd set that one up. If we look at this next equation, again, we can do this fairly similar, but again, maybe I'll give you a moment to pause if you want to pause and try working through this at home. Okay, assuming you pause or need a little more scaffolding before you get going and trying on your own, can I have a scenario where we have torque from one individual causing it's like counterclockwise torque, and this other child here is causing a clockwise torque along this center axis point, okay? Now, the big clue with this question is that these two are in equilibrium. So we know the torques and the forces involved in one direction, clockwise, let's say, are going to equal those in the counterclockwise direction. So what do we do with this? Well, and we have two different R values potentially, right? So how do we figure this out? And I'm sure we've all had this scenario, as kids playing on the seesaw, you know, maybe one of your friends were larger and had more mass than you or less, and you play around with like, okay, do I go closer? Do I go farther? How can I keep the other person in the air without letting them come down? Stuff like that. So now you can actually like go back and you could have calculated this, and knowing this, um, maybe use this information to your advantage for next time you're at the playground, I guess. So here's how we're gonna set this up, or I'd suggest to set it up. You essentially have one side equal the other side. So another way I could do that is I'd say torque one, and this little t is like a little squiggly t. It's called tau. So torque one equals torque two, or torque, yeah, and that would be like this child equals this child, sort of thing, for the torques they produce. And then kind of next line below that, I'd write in there are F values for each of them, right? And so when we get to that point, um, I can say, oh, my R value for one looks like it's given to me. It's 1.6 meters. Do I have my R value for two? No. So that's my unknown I'm solving for. Okay, well, what about my forces? Well, I look at that and I don't see that their forces are directly given. So what I can do from that is I can substitute in for my force, my weight value, and I have mass times gravity. So child one's mass is 26 kg. I can multiply that by 9.81, and I'll figure out what that force is or that weight is, right? I can substitute that in, right? So that's that downward force occurring is a weight. So once I have that, I have all my values for the torque from side one. And because it's in equilibrium, I know torque two must equal this. So the only missing value I have really is the force. I know the force is mass times gravity. So essentially M is my, I have the mass. So I can calculate the weight force for this individual, but I don't know the R value. How far out is she from the center pivot point, right? I don't know. So the R value for torque 2 is my unknown. So I take the force from this individual, the weight, and divide it from the torque on this side, and that will give me the torque on this side. Okay, again, if you could follow along with the verbal version while you're writing it and following along, great. If not, I'll post a PDF kind of showing how to solve that one. Okay, okay, great. So that was torques. And I think the setup, just to kind of clarify something, the setup of torque on this last practice question is really, really important for moving forward and trying to solve torques through a whole bunch of our torque kind of equations that we'll come across. Yeah. All right, well, let's talk about the moment of inertia. All right, so moment of inertia, kind of a new topic, but it's still involved with rotation and um, kind of how rotation occurs is more related to mass. So if we think back to our initial understanding of inertia, right, Newton's second, um, what we tend to think of is inertia is related to mass. So the more massive something is, the more likely it is to resist a change in motion by external forces. It's also more likely to continue its current motion based off of its mass, right? We see a very similar thing when we're talking about moment of inertia, which is rotational inertia. Okay, so we see this kind of proportionate inertia due to its mass, but we now also have an R value. So the distance of that mass from the center axis will increase by a value squared, so squared value, how much this moment of inertia an object has. Okay, so yeah, let's just kind of cover the SI units. Mass is in kg. Our R value is in meters, and it's meters squared. So when we're talking about moment of inertia, we're talking about kilograms per meter squared. Okay. Now, there's a couple of different ways we can visualize this, and you've experienced this in your life. We're going to go through a couple of examples of that. And I just want to say that this version of our moment of inertia, and we'll just use this as a kind of standardized approach to this. So we're always going to use mass equals r squared. We're just going to assume that all of the mass of whatever object we're dealing with is within this kind of point. So we call it a mass point or a satellite, right? So this kind of object moving around an axis point that isn't connected. But for us, when we're talking about our body and body, um, rotating around things and stuff, we'll kind of consider this. Now, is that always true? No. And again, you don't have to memorize all these. In theory, we can look them up or I can provide them to you, but um, you could try to work this into your RPA4 if you really wanted to, but ultimately, I just want you to be aware that depending on how an object is shaped, will change the fraction of its mass that we deal with. Okay. So why does this kind of matter as a concept and why I want you to at least be aware of this? Well, again, it's the mass and how that mass is distributed around or away from the center pivot point or the axis point that matters for the rotational resistance, right? Or rotational momentum, right? Sorry, inertia, right? So again, inertia is the capacity to resist a change of movement or to continue it, right? And in particular, we're talking about rotation when we're talking about the moment of inertia. So if we can just think for a moment, if something is rotating like a disc, like a hockey puck, stopping that rotation is going to be a little bit easier than a scenario where all of the weight is pointed really, really far away from that center. Okay. Let's look at a slightly different example to kind of clarify that a little bit. Okay. So if we have a barbell, and you can kind of picture yourself standing in the middle of it and trying to rotate it on the floor, let's say it's just rolling. You got the bumper plates on there and stuff. If you try rotating in the middle, and obviously you're moving your legs out of the way when you do this, being able to turn it from the middle is pretty easy. It's not the hardest thing, but it's relatively easy, depending on what sort of weight you have on there or how much mass is present, right? If you had that same barbell with the same amount of mass, and instead of being in the middle and trying to rotate it around the middle, you go to the one outside. And again, with that same amount, just say one hand, you try turning the barbell on the floor. Okay. That's going to be significantly harder. Okay. Because what we end up having is instead of half of the R values, and again, remember our R value is squared here in the moment of inertia, we're going to get double that length. Okay. So the other way, and again, it's rolling on the floor might seem a little bit easier, but if you try thinking about lifting up the barbell from these different points and then rotating them, it becomes very obvious which one's harder, right? So pick up a barbell from the middle, you kind of have that balance, so like you can get it moving through this angular velocity as we see here in omega from the middle, a little easier to overcome here, much, much harder, right? It's very challenging to lift the barbell up from one end because it's the R value, it's the distance away from where you're trying to pick it up and rotate it that makes this mass seem so, so much harder to get moving, right? You need so much more external mass. So if you want to put numbers in just to kind of see that this is true, if you know that the moment of inertia, this capital I, is the sum of all our masses times the distance at which that mass is from our pivot point, so our R squared. When you actually put some numbers in, mathematically, if this is the same, we can say this is 2 mr squared. But again, if we put this at the 0 point and we make this 2r versus just 1r, so we double the distance just on the one side, we actually, because it's squared, we get 4mr squared. Okay, so again, kind of doubles on us there. Okay, hopefully those illustrations kind of helped a bit. Again, if we just kind of look at this equation, the most important thing when we're talking about moment of inertia is our R value, the distance at which our mass is distributed away from the axis point. Okay, cool. Let's talk about conservation of angular momentum. This one's very, very common in sport and how we move our bodies. And of importance, also uses moment of inertia. So kind of builds on the concept that we just finished speaking about. Okay. I think when we're also talking about angular momentum, and in particular, it's important to note the conservation of angular momentum, because that arises a lot. Okay, let's dive into it with some examples and see how this goes. Okay, so if we have our moment of inertia, or sorry, we're talking about angular momentum. Again, here's our moment of inertia, and is multiplied by the angular velocity that an object is traveling at, and that equals our angular momentum. So again, looking at the SI units of each of these, if you recall, our moment of inertia was kilograms times meters squared, right? Our mass times our R squared, mass kg, meter, or R value is meters squared. So the distance from the axis point to whatever our mass is. So that's our moment of inertia, this capital I. And then how fast rotationally that's traveling, right? Now, if we think back to just, I'm going to say regular momentum or linear, right? It's our mass times velocity. Well, same thing here, right? More or less, it's our mass accounted for in the moment of inertia times our angular velocity, right? Okay. So again, our mass times velocity. Again, to just try to drive this point home, I've said a couple of times, it's our mass times the R value squared. So again, the distance at which that mass is distributed around the axis point is really, really crucial. Here is why. Okay. Got a few examples, but I'll try to just stick to this one. If we consider, for example, a person rotating in skating, okay, figure skating. When they go to start a spin or even when they're rotating in jumps, what we see them do is distribute their mass as far away from their center point as possible, right? So if this is their center point, center axis of rotation here, we see they have some angular velocity here. We can even just call it 1 unit of angular velocity at the start of the system. And this is our starting position of our system that's going to be rotating, that we are going to see angular momentum conserved in. Okay. So we have some set angular velocity, and our, again, moment of inertia, or our mass per r squared, is really far away. Okay, so if L stays the same, and we decrease our I value, now remember that's got two parts, our mass and our r squared value. So if we decrease our moment of inertia by, we can't get rid of our mass, right? We can't just in some ways we might be able to in some scenarios, but typically in sport and with our bodies, we don't just lose mass instantaneously. So what we're doing here is we're not changing our mass, we're changing our R value. Remember, R value is squared. So in a squared fashion, if we decrease our R value by pulling in our arms and legs, so we square decrease our moment of inertia, we will see a proportionate increase in our angular velocity, because in the start, so initial and final moments of our scenario here in our system, which includes this person and their angular momentum specifically, in the start and end, the L has to stay the same. So again, if we see a decrease in our moment of inertia, we see a proportionate increase in our angular velocity. because our angular momentum must be conserved. Okay. Might have sounded a little repetitive there, but really trying to drive that point home, okay? Because this is how we use this so often in sport and physical activity and how we move our bodies. It's just really, really common. So again, wide mass, or sorry, high R value with our mass to low R value with our mass. Why am I talking about R value? Because that's part of our moment of inertia, which therefore increases our angular velocity. Okay, other times that we see this occur is when we go to throw balls or when we're running, and essentially anytime that we try to make things easier to move. So we want to decrease our moment of inertia. We pull our limbs in close to our body and we decrease that R value. We start the rotation going, and then as the rotation continues along, we do increase that R value, but our angular velocity has already been high and we follow through. Okay, so again, to get over the moment of inertia, we shorten our limbs and then we lengthen them to, for example, maximize our endpoint velocity of releasing a ball. So that'd be a throw. We were running to be more efficient with the weight of our legs or the mass of our legs. We pick them up into triple flexion, they come close to our body to allow an easy swing or leg movement as it comes through. And then we extend to meet the ground and pull through with a lengthened or fully extended leg. Then once we push off, again, we go into triple flexion. So a bend at the ankle, knee, and hip to conserve our angular momentum by shortening our R value, increasing how quick and relatively less force needed to move the leg through before we extend it and pull back. Okay. So again, hopefully those few examples, you can start seeing how conservation of momentum crops up in so many activities and how we move. Okay. Okay. Great. We are pretty much at our last question here. So great, we made it. Again, I'll post a work through on this as soon as I can. But to kind of set you up, at least scaffolding. Again, you can take a moment to pause now before I start explaining. Good. Okay. And I'll start scaffolding a little bit. You can pause at any moment that you want to try working through on your own. Highly suggested. Um, yeah, so here again, it's not dissimilar from some of the questions we've done earlier, where as you read through, you might clock that you're like, okay, this is conservation of angular momentum. I know the position 1 and position 2 of this child, position 1 to position 2 of the child, the angular momentum of the system is going to be conserved. So I can have my L1 or L initial equal L2 or my final LF position, okay? LI, LF, initial and final, right? So I can start with that. I literally write L1, L2 for initial and final. Then I can start filling in the variables and plugging in the variables that I know, right? So below that line, I can go, okay, my moment of inertia equals my angular velocity. Do I know any of those variables? Well, no and no. Okay. Oh, here I have some angular velocity. Great. So initial angular velocity, 2.2 radians per second. Great. Do I know this moment of inertia? It's not specifically given to me in kilogram meters squared per second, but I do have kilogram meters second, or meters, kilogram meters squared. Okay, so I don't have necessarily the rate, the per second part. Okay, so I can figure that out because that's what that will equal, right? So I take this, calculate it out, and I can get my I value for the starting point, right? I have my distance, my rotational speed, and I have the mass of the child. Good. All of this is information so I can plug in. So I do have my L1 or L initial point, the starting point. Now I have that equal directly L2 or my final point. So I have my R value, I have my mass, I don't have my angular velocity, but that's what I'm trying to figure out. So when I have my moment of inertia for my final state or my final position here, my L2, I can divide that from whatever my L1 had equaled, and that will give me my angular velocity for the final position in the system. Okay. And again, the whole reason we can make L initial equal L final is the concept of conservation of angular momentum. I should say momentum there. Okay. Conservation of angular momentum. All right. Okay. Again, if you can follow along verbally, I'll try to post a PDF of the work-throughs on those. Yeah, and I think just kind of as like a final thought and something to leave you with, we have linear and rotational motion, and they all have analogs to one another or similarities, right? For linear, we had position. For rotational, we have angular position. We have theta or radian in particular, right? Radians. Velocity, we have velocity. Here we have angular velocity for angular motion with omega and kind of so on and so forth as we make our way through. Today, we spoke about how mass is kind of this linear inertia, and our moment of inertia is mass times our R value squared, but they're analogs of one another. And even with our momentum and angular momentum, we have similarities there between the two. So again, hopefully you're kind of seeing that kind of pattern that has shown up between linear and rotational motion. Okay. There's some practice questions here. You can work through them. Again, please pause here. Try to go through them yourself. It's a good review. Give you a couple of seconds for that, just to have a chance to pause if you're doing something else. Okay, and then to kind of work through, for question one, you have this force, 60 newtons applied perpendicular to a wrench at a distance of 0.4 meters. Great, both SI units, stoked on that. Calculate the torque. Well, we simply go to our torque equation. But we have two. Which one do we use? Well, knowing that this is done perpendicular, or sorry, that the force is applied perpendicular, we can simply go with the simplified version. We don't need sine theta. We go just 60 newtons times 0.4, and that will give us our Newton meters for our torque. Okay. For question two, explain why a gymnast can spin faster when tucking their body during a somersault. Well, again, we think back to our conservation of angular momentum, or capital L. We have our moment of inertia, which is the breakdown of our mass times our R value squared. So typically gymnasts will start at a like standing position, and then when they go into a somersault, that's a tuck position. So we're decreasing the R value by a squared sense. We are decreasing our moment of inertia, which is capital I, if you remember that. And therefore, because we have capital I times our angular velocity, that will equal our um, um, angular momentum. And because it's conserved, we see an increase in angular velocity, okay, with that decrease of our R value. All right. And then last but not least, we kind of have another similar question to the ones we've been doing today, where we have a diver spinning mid-air. We're giving their angular velocity in radians per second. Great. And we're given their moment of inertia. Great. So if we're talking about momentum and conservation of momentum, we're already given all our values there. We don't have to go look at the mass and the R value like we were doing for the last equations. And here we have 6 kilogram meters squared for the moment of inertia once they've opened up. Okay, so we start from a spinning position, either along the axis or like in a somersault. And from there, what we'll have is 4 revs per second times 3 kilogram meters squared. And then we can essentially divide that by 6, which is going to be in our final position, and we will get our new angular velocity. Okay. Whew, okay, so that's a lot there. Here's all the equations that we got to see today, and that concludes today's lecture. Again, please feel free to email with any questions and set up office hours as always. Cheers.